Let's see, is this one working? All right. So now we have the most exciting part of the agenda today. We have student and staff researcher lightning talks. So last year when we did this, we asked for feedback, and one of the most common bits of feedback we got was we love the lightning talks, keep the students on the agenda. So we're going to do that again. If you're a student or staff researcher, please come on up and kind of be nearby so that when your slide comes up, you can jump up here. We have a few students who have posters in the poster session after lunch, and then we have quite a few students who don't have posters in that poster session. So please do feel free to come up to the students afterwards, ask them questions, and offer them jobs, that kind of thing. Just let them graduate first. We have too many people poaching our students and wanting them to leave while they're still students. So.
Well, hello, everyone. My name is Nick Crenshaw. I'm a graduate student here with the nuclear department. I'm a PhD student here at the nuclear department here. I'm working with Dr. Charlton and a startup company called Gen Alpha Nuclear Technologies on a metal carbide foam-based neutron sensor for high-temperature reactors. Okay. So Gen Alpha and UT are collaborating with experimentation and modeling on a foam electrode-based neutron sensor systems for high-temperature reactor systems. Interestingly, this is funded by the National Science Foundation. These sensor systems use metal or ceramic foams and reactor radiation to produce what are called nuclear-excited low-temperature plasmas, through which electrical currents can be used and extracted to actually detect these neutrons. This this detector would be designed to operate between 300 and 1100 Kelvin, and again, can be used in high-temperature reactors. There's also a possibility of using it for direct energy conversion for space systems. So what's been done so far? Spatially dependent neutron and gamma fluxes incident on the foams during reactoration at the trigger reactor here at UT were modeled using MCNP's unstructured mesh feature. The foams that were modeled were hafnium carbide at 10% density and then graphite at 3% density at temperatures from 300 Kelvin to 1100 Kelvin at 100 Kelvin intervals. They were treated as macro bodies, quote unquote, and approximated as annuli, which are cylinders with a hole in them basically, of uniform density. This is an appropriate approximation because the pore density of these materials and foams, I should say, are significantly lower than the actual mean free paths of the material. What we found so far is that in irradiation, you will see a slight left to right gradient in flux across these devices, but there's no temperature dependence, which is expected. What we've concluded from this is that the NETL reactor provides sufficiently high neutron and gamma fluxes in the BP1 beam port in the reactor for NLTP production and therefore device testing. Future work on these will involve using micro-scale models to create actual geometries of these foams and then model the charged particle transport through the foam and into the plasma that will be created. And of course, experimental device testing in the reactor. That's all I got, so thank you.
Hi, I'm Bradley Gladden, and I'm a graduate student at UT Austin in the nuclear engineering program. I'm presenting over my poster, which is a project where I modeled fluorinated spent nuclear fuel in a molten salt reactor. So the reason I did that is because right now, spent nuclear fuel, when we take it out of a reactor, is considered waste, and there is actually a lot of energy that can still be produced from it. Right now, we don't do that because in order for that to be efficient, we would have to use traditional reprocessing methods, which remove all of the extra stuff out of spent nuclear fuel and leave just the uranium or sometimes plutonium, and that creates a lot of issues. It's a very energy-intensive process. It produces more highly concentrated, highly radioactive waste, and it also has a proliferation risk since the uranium is separated. So what I did was I designed an experiment to convert spent nuclear fuel into a form that can be reused in a molten salt reactor without the need for reprocessing. So my experiment design I use nitrogen trifluoride to replace the oxygen in spent fuel with fluorine so that it can be dissolved in the fluorine in the molten salt reactor, like the one that we're building in Abilene right now. So this process leaves as much in the spent nuclear fuel as possible, all of these extra products. It creates less waste since we're keeping as much together as possible, and it's more proliferation resistant because of that. So my poster that I'm presenting on is, I'm modeling the results from that experiment in a molten salt reactor in order to observe the reactivity effects that spent nuclear fuel in a reactor has, and then adjusting the composition and geometry in order to optimize those effects. And basically prove that it's a feasible way to recycle nuclear waste and still produce energy in a reactor. So if that sounds interesting to you, please stop by my poster and I'll tell you how I did it.
Hello. My name is Harrison Reisinger. I'm a PhD student in Dr. Clarno's group. And I'm going to be talking about sensitivity and uncertainty quantification for nuclear systems. And I'm going to be using that, I'm going to be using Dakota to do that. So my motivations here are essentially to reduce the cost of building nuclear reactors by being able to loosen tolerances in build and material aspects and like the inputs to your reactor. The sensitivity analysis really identifies specifically what inputs are the most responsive and take the most effect on the outputs. Your uncertainty quantification is propagating that input error to the output error, so you can have a better understanding of your error in this response. So for instance, you can look at the temperature feedback, how much the reactivity goes down as temperature goes up, and then you can quantify that error bar a lot better by taking into account all of the input uncertainties. An application for it is the molten salt reactors. The reason why is specifically because most of the input uncertainties are known, but it's not very trivial to get the output uncertainties. So what that means is you can conceptualize somewhat on, I could believe this input uncertainty affects this output, but you can't directly say one-to-one, and it's very hard to find a deterministic equation that can do that for you. The rest of the slide is just molten salts are really cool. I used to work on the MSRR, and now I'm doing my PhD. So I'm using Dakota to do the input-output simulation management, essentially. So what Dakota can do is create, say, 600 inputs, each with like a slightly different input variable, and then run your simulation and then get the output. And then you can get stuff such as sensitivity analyses, which would be Sobel indices. You can also get just the response out. So if you want to look at just creating a humongous parameter study, you can do that too, as well as the uncertainty quantification. It's able to compile all of that output data together. I created a very simple 1D neutron transport code. On the top images that you can think of that as the neutron population. So on the left, there's a source in the middle and it kind of spreads out. And then on the right side, there's a source coming in on the left, and then you can see it drop off. On the bottom, those are currents, so that's kind of direction that the neutrons are going. But using that with Dakota, you can basically quantify or identify the inputs importance on those outputs. So on the left, we're looking at scatter reaction rate, and you can see the green one, that it basically your cross-section for your scattering is very, very closely linked to your reaction rate and scattering. And on the right, you can look at what's the value of the flux on the right side. And you can see the phi, which is the flux boundary condition on the right, is much more important than the one on the left, which makes sense if we look at this image. Like, it basically goes to 0. So that's pretty much my talk.
Okay, last year I went a long time, so this is gonna be fun. Do we get to see it? Should I click something? Oh, there it is, never mind. Okay, hi. This is my poster I'm presenting next door, so come see me if you want to hear more about it. I'm Rachel Seidel. I work directly with Dr. Haas as a graduate student here at UT. My project is using this decision-making model for the Texas grid called GenX that was developed by Princeton and MIT. The specific model of Texas I was using was designed by the Weber Energy Group here at UT. So the goal of this is basically, we need more power in Texas. We're going to need more power in Texas increasingly in the next many years. And I think that nuclear should be the thing to fill that. So here's modeling what that might look like. The main goal of this specific poster is to show what price point we need to hit for nuclear to be viable and competitive in Texas versus other powers, baseload powers like natural gas and coal, but mostly natural gas. So in this bottom left graph, we've got, first, here's GenX, top right corner, 16 regions of Texas modeled. So I can put a nuclear reactor in one of those 16 regions and see the different ways that that location impacts the price and deployment and everything. So in this bottom left, we've got all these different regions. Each different color line is a different region. X and Y for all of these graphs is going to be the cost in CapEx, capital expenditure, so dollars per kilowatt, with the Y being the amount that GenX decides is viable, is competitive to deploy. So I'm modeling 2030 in all of these, the 2030 like load values. So we can see we've got a lot of variation in how much it's deploying based on the region in each color. Those top 3 lines that I look at a lot specifically are San Antonio, Houston, and Dallas. So this top middle one is me modeling a reactor in Houston specifically. So as the CapEx of nuclear increases, we see that it deploys less and less. It becomes less competitive versus something like natural gas. So this last section in green, that's nuclear, that has a lot of nuclear deployment is $3,184 per kilowatt, that's after applying discounts that you can get from the IRA tax credit, from the ITC investment tax credit. So that's about 50% reduction. So that $3,184 per kilowatt becomes $7,400 per kilowatt in like upfront costs. So that, according to this in 2030, is the price that I think we need to hit for nuclear to be viable. That's about 84% of what the National Renewable Energy Lab thinks it is right now. This bottom middle graph is basically the same thing, but instead of increasing nuclear costs, I'm increasing natural gas. So we can see that nuclear starts to outcompete natural gas when it's at about 2.5 the times the price natural gas is right now. So this is interesting because we think that natural gas is going to get more expensive the next few years as competition increases for these really expensive turbines we need. We might need nuclear to come in and outcompete that baseload power we need. So in conclusion, I think nuclear needs to get 84% less expensive by the year 2030, and then we can really start having some competitive, viable nuclear in the Texas grid. You want to hear more about this? Ask me some questions. I'll be next door.
Hi, everyone. I'm Mike Sheridan. I'm in Dr. Charlton's lab, and we're looking at the circuit effects or radiation effects on integrated circuits in combined or ordered environments. And specifically, we're looking at the LM741 integrated circuit, which is like a very small microscopic, maybe like a millimeter wide. Oh, I'm sorry. Well, there's not much on the other slides. So, anyway, sorry. It's a very small circuit that's like a millimeter wide, and it's fabricated all at once at a facility, and it's used in many circuit applications. And we're kind of just doing a basic framework to see if synergistic effects are occurring on electronic devices at the circuit level in combined environments. And what we mean by synergistic effects is like if I have one damage mode that degrades my device by 20%, and then another damage mode that that degrades it by another 20%, is that value going to be different than 40%? And what we found in our work was that sometimes it was greater than 40%, depending on the ordering, or not 40%, but it was greater than the linear sum, and sometimes it was less than that linear sum. And it is a little bit complicated, and it's not as clear-cut as we thought we would see with the curvatures. And so, like, the two effects we look at are total ionizing dose, which is going to be like gamma rays and X-rays, and the other one is going to be displacement damage, which is like neutrons inside a nuclear reactor. And what we do is we irradiate the circuit at one facility in the reactor, wait about 4 days, and then irradiate it in the X-ray environment. And then we flip the ordering, and then we see if they differ. And if they were linearly summed, they should be the same. In our case, it wasn't. And then further work for this is we built a large version of that circuit in discrete components that you can buy at like DigiKey or Radio Shack. And so we built that circuit, and then we're going to, while the circuit is constructed, only irradiate certain parts of that component to see if certain components are more susceptible to radiation and the overall output of the circuit. Thank you.
Thank you for the introduction. Hi, everyone. My name is Pranshu Adhikari, and I work with Dr. Haas on nuclear explosion monitoring things. And my work, which you can't see up here, but I promise it exists, it's looking at the radioisotope signatures that we get from a complex venting of fission products from an underground nuclear explosion. So when an underground nuclear explosion happens, these fission products will move throughout the underground surface of the Earth. It'll vent up to the surface and then release into the atmosphere. And current systems that look at that monitor for these explosions look at a very simple release of these fission products, but what we want to do is try and figure out if we can kind of have a more rigorous evaluation of these releases, what those isotopic signatures could look like, and if they would differ. If you'd like to talk more about this, please come find me. I'm very happy to do it. Yeah, thank you.
I also do not have a slide, so you'll just have to listen to me talk. My name is Colton Mathis. I'm a first semester graduate student here. My project is over the chlorine-35 NP cross-section, integral cross-section. So basically the reaction rate in chlorine salt. It is really important, especially as we get into this we've talked a lot about molten salt reactors during this talk, and there are certain molten salt reactors, particularly the MCFR, that are molten chloride fast salt reactors. Now, what that means is that you have a fast neutron spectrum, which, interestingly enough, prior to 2024, there was 0 data points in the fast neutron region for this reaction, which is one of the main reactions, charged particle reactions for chlorine-35. So it's really important to be able to verify that those measurements were correct, as well as put bounds. A lot of the ones, as you get into the epithermal region, have really large errors that are associated with them, and that will both slow them down going through the licensing process, as well as make it more difficult to control, / more difficult to predict the corrosion effects that are going to happen on some of those materials. So I'm utilizing an in-core radiation facility that was developed for nuclear explosion monitoring purposes, to create a fast neutron flux, irradiate my salt, and then because I'm not as insane as I probably could be, I'm not doing proton spectroscopy, because that would make my life, unless Derek wants a grad student for 15 years, which I don't think he does. I'm doing beta spectroscopy on the sulfur-35, that is the production, or the isotope that is produced via that reaction.
All right. Hello again. My name is Eric Weiser. In case you missed it earlier, I am a full-time researcher here at UT, and I'm also a part-time PhD student. The slide didn't come through, unfortunately, but the research I was going to discuss is I built out an economic model analyzing the viability of building a nuclear reactor, a new set of nuclear reactors here in Texas, and I wanted to look at policies that affect the implementation of new reactors. What I wanted to do was identify what you could call the best bang for your buck policies or policy changes. So which policy changes would cause an outsized positive impact on the construction of these reactors. An easy one off the top of my head was something as simple as the state of Texas giving a firm commitment that they will be building more reactors and they will be helping companies and corporations build reactors in Texas. Something like this reassures financial investors and financial institutions that the state is serious about this. This can cause a decrease in discount rates and decrease in interest rates associated with the loans that are required to fund these projects. And that, removing a lot of that interest removes hundreds of millions of dollars potentially over the lifetime of the project. If you'd like to hear more about this, you can come find me. I can send you the abstract for this paper, or if you're feeling keen, you could attend my presentation at the International Association for Energy Economics Conference in Paris this June. Whichever's easier. Whichever's easier for you.
All right, that wraps us up for the scheduled presentations. I'd like to thank the Energy Institute for inviting us to join them here at Energy Week. This has been amazing. Thanks to Brian Korgel, to Laura Black, Lisa Hernandez, all at the Energy Institute, and from Andrea Melendez and Kaylin Donier in our group. They have done a huge lift to help us be able to do this. I'll say we are frustrating collaborators because so many people want to learn about nuclear. I'll say, 7 years ago, maybe eight years ago, I was an untenured professor, and Dr. Landsberger and I were the only professors left in our entire program, and I was really concerned that the school might just say, you know what, we don't really need nuclear energy at all, so let's just wrap up this program and move on. And now the growth has been amazing. So our sponsors have been great. Support from the state's been great. There's a huge amount going on at the state level, and we see a very bright future for nuclear energy and other applications of nuclear technology at UT. So thank you all for your interest. We look forward to chatting afterwards, and have a good rest of Energy Week. Thanks.